Hello everyone, welcome to Skilled Dev. Trey here, and in this lesson, we're going to learn about arrays. Arrays are one of the most important and popular data structures, both in coding interviews and on the job. We use arrays all the time when we write programs, so it's essential that you fully understand them when going into your coding interviews. So when we declare an array, it creates this list of items, and the items are indexed. We start at 0, which corresponds to the first item, and then each item after it is sequentially indexed up to the last item. So, when we declare this array, what our programming language actually does is map these items directly to memory. So it finds the number of empty spots corresponding to the number of items in the array, and then stores these items contiguously. So all the items in the array must be one after the other, exactly in the order as we declared it originally. And because we have this mapping from the index to a memory slot, we can actually access the array in constant time. So the programming language knows exactly where to find this array in memory. When you say, for example, give me the item at the third index, it knows to directly go to memory slot 421. So having this structure and indexing can be a huge benefit. It gives us this logical, linear nature and allows us to quickly access items at an index. So one of the important aspects of arrays is understanding when we get fast operations and slow operations. We get fast operations when we add an item or remove an item from the end, or also known as pushing and popping. And we get fast operations when we access or update an item at an index. So when we push a new item or add it to the end, this only takes one operation, so it's constant time. We have a free slot and simply add this item to it. So in memory, the programming language just added this item to the end in the last open slot. Then, when we remove an item, it's again constant time because it only requires one operation. So our program calls pop on the array. Then the programming language just removes the last item from the list in memory. So when we add or remove the last item, we don't have to change anything else in the array. The last item is already at the correct index, and none of the others are required to be updated. We simply add and remove it from the last slot, and then the programming language does the same with the item in memory. But there are some slow operations in arrays that we must be aware of, and that's when we try to insert or delete from anywhere else in the array other than the end. So let's insert the item Tesla at index 1. To do this, you must update the index of all the items that come after it. So in the worst case, it's going to require O of n linear time operations. And because items must be stored contiguously in memory, we must move them all forward by one slot so we can free up the space for the item we're inserting. So we added Tesla to the array, and we incremented all the indexes that now come after it by 1. So our programming language also shifted these items by one slot in memory. Now let's remove Amazon at index 2 in the array. So we clear it from memory, but now we have this open slot, and our array must be continuously indexed and be stored continuously in memory. So we must decrement the index of all the items that came after it to maintain the indexing. And this corresponds to shifting all the items back one spot in memory. With arrays, we get fast operations at the index. So to look up an item or access it by index is constant time. Or if we want to change an item at an index, it's constant time. However, to insert or delete an item from anywhere other than the end is going to be O of n linear time. We get this O of n time because we must keep the array ordered and correctly indexed. So if we insert or delete an item, we must update all the indexes that come after it. However, we can append or push an item to the end of an array in constant time because we don't have to update any indexes. We're just adding one item to the end. However, if we prepended, this would take O of n linear time because we would have to update the index of every item after the one we're adding. The pros of using an array are that it's ordered. The items are sequentially ordered from the beginning to the end. Another huge benefit is that we get fast operations at the indexes. Since we can access an item by the index in constant time, this can be a huge benefit to improving our solutions. We can also insert or remove an item from the end in constant time, which is known as pushing or popping an item. And finally, we can represent higher-level data structures using arrays. So for example, we can take two-dimensional arrays, where we have arrays inside of arrays, to represent a matrix. A con of arrays is that we get slow inserts and deletes. If we add an item anywhere within the array, we must update all the indexes, so this takes O of n linear time. We also have slow searches with arrays, so if we want to find an item, we have to iterate through all the items to find it. So this will take O of n linear time, but later we'll actually see that we can improve on this with binary search if the array is sorted. And finally, indexes are not flexible. We must pay the cost to maintain them, and an index may or may not have meaning to the actual item there, so it's simply a number that represents that spot. And one final thing I want to note is that there are two types of arrays: static arrays and dynamic arrays. Dynamic arrays have started to become more popular in coding interviews, and in some languages, it's actually the only choice. For example, higher-level languages like JavaScript or Python only allow you to use dynamic arrays. But in other languages like Java, it's possible to initialize an array with a fixed size. So you can only add items until you reach the end, and then the array is full. With a dynamic array, what happens is that as the array gets filled, the programming language continues to free up more slots so you can add more items. And the most common implementation is to just double the available space every time you fill up an array. So dynamic arrays have a lot more happening underneath the hood, but they're completely controlled by the programming language, so it makes it more simple for us to work with as developers. So we can see here that every time we add an item that fills up the available capacity, the array doubles in size. So we have 2 declared with 1 empty slot. We add 7, the array fills up. Then we try to add the number 1. Well, the array isn't large enough, so it doubles in size, and then adds 1 in the 3rd slot. We add 3, and the array is full. Then we try to add 8. This is larger than the available capacity, so it doubles from 4 slots to 8 available slots, and then we add 8 in the 5th slot. Then finally we add 4, and have 2 remaining slots. So the logical size, or the length of the array, is the number of spaces actually used. However, there is a larger capacity that we continue to increase as we continue to fill it up. And you'll notice this turtle, which means we have a slow operation. So when we fill up the array, we have to find a new spot in memory that can fit the new array and copy all the elements over. So this takes O of n time. And then you may wonder, how is pushing an item constant time if we have these O of n operations to increase the size of the array? And this is a concept called amortized time. And what happens is, most of the operations are constant time. As long as we have available space, we can push in constant time. And then on a very rare occasion, especially when the data structure is large, we have many items in it, we very rarely perform this O of n operation. So imagine we have an array with 1 million items and then a million free slots. We'll continue to push to these free slots in constant time for a million operations in a row until we reach the full size. And then to free up space, it's going to copy all these items over and then add additional space for us. But what happened was we pushed 1 million times in constant time before we performed this O of n linear time operation. And with amortized time, these fast operations actually outweigh the one very slow operations because they happen much more frequently. So we assume we can still push in constant time even though on a very rare occasion we do perform this O of n linear time operation to create more space in the data structure. And that's the foundation for arrays that we need for coding interviews. Thanks everyone, and I'll see you in the next lesson.